So this is on page 13 of your unit handout. We're dealing here with stretches. What we're going to do tomorrow is put everything together. We've been looking at translations, that's the H and K thing, kind of in isolation. And then we've been looking at reflections in isolation. We haven't combined anything yet. We haven't said, well, what's going to happen if I reflect and then translate? Well, today we're going to look at a third type of transformation called stretching. And then tomorrow we're going to put all three together. We're going to be looking at reflections, stretches, and translations tomorrow being applied to a single function. So if an original function is stretched by a certain factor relative to either axis, we should be able to graph the resulting function. If you're given the right information, you should be able to come up with the equation of a resulting function after an original function has been stretched, either horizontally or vertically. And then, much like reflections, there will be invariant points from time to time during stretches. So I want to go through the terminology here. And I looked quickly this morning at your note package, and this might say something different, but I think it might say general terminology, but it doesn't matter. This is the terminology. Just to go back to what we've learned so far, a translation means you move the graph left or right or up or down. And a reflection, of course, is what we looked at yesterday. These are transformations that change either where the graph is or which way it's oriented. Because a reflection will turn something upside down relative to the original thing if it's vertical, and it will flip left and right. Reflections will if it's horizontal. A stretch is so in a translation or a reflection, the shape doesn't change. The size of the thing doesn't change. It's just the orientation of where it is. A stretch will change the shape of the graph. Stretches will make the graph larger or smaller, and you want to be careful with that, because when I say larger or smaller, it can make the graph larger vertically, but not larger horizontally. In other words, it can stretch it vertically. Graphs can be stretched horizontally, or they can be stretched vertically, or they can be stretched both horizontally and vertically. And if you imagine taking an object and stretching it horizontally and vertically, I'm not saying it has to be stretched by the same, what we call factor. It might get twice as tall, but only 1.5 times as wide. Now, first of all, if you read this goes against the English language here, because the word stretch in English would mean to get bigger in some way. But in mathematics, a stretch can make something bigger or smaller. So a long time ago, we used to use the word stretch if I took a graph and I pulled the ends away from each other, and we used to use the word compress if we pushed the ends together. But we always use the word stretch. In either case, we're talking about stretches. I will sometimes say if a graph gets taller, then it's an expansive stretch. And if a graph gets shorter, it's a compressive stretch. But those are not math terms. That's just me trying to put an adjective to something for you. The vertical stretch factor determines whether the graph increases or decreases in height. Okay? So basically, before I look at a little diagram here, if the vertical stretch factor is 2, the graph will be twice as tall. It's going to be 200% as tall as it was. If the stretch factor vertically is 1/2, which is 0.5, then the graph is only going to be 50% as tall. It's going to be 1/2 as tall. So the stretch factor is a number. It's a positive number that tells us basically what you're multiplying the height of the graph by to get a new height. And stretch factors are never negative. Now, if you were to pull up the files for your textbook, sometimes they will talk about a negative stretch factor. I don't think you should. A stretch factor is a positive number. And a stretch factor cannot be 0. So the dark line here on this diagram is telling you the domain of values that we could have for a stretch factor. It cannot be 0. I mean, I guess it could be 0, but then the graph disappears vertically. It becomes a height of 0. There's nothing there to look at. We say that the stretch factor can't be 1. I guess it could. All that means is it's not stretching, because 1 is 100%. So if the stretch factor is more than 1 vertically, then the graph will become taller, and if it's between 0 and 1, which would be a percentage between 0 and 100%, it's going to get shorter. You guys with me on that? Okay. The same kind of thing applies to horizontal, but I guess I'll show you this first. If that's an original graph, and this is the transformed graph, and you will, don't worry about the fact that they are displaced from each other vertically. I'm just asking you to look at the heights of these things, okay? Trust me, if I were to get out a ruler and measure how wide each of these are, they're both the same width. So this has been stretched vertically. And when a graph gets taller in this fashion, I'll use arrows that point away from each other to indicate that. And can you just trust me that if I measured the height of the original graph and I measured the height of the new graph, or picture, I guess it's not really a graph, the new one is twice as tall? Okay. If I take this original thing and I do that to it, I hope you can see visually, and I don't need to get out a ruler to demonstrate this. It's the same width, but it's shorter. So this is a vertical stretch. It's a stretch in mathematics language. But in order for me to communicate to you what's happening, I draw two arrows that are pointing towards each other. Right? So if you look at the arrows here, they're pointing away from each other because the thing is being stretched end away from end. Whereas here, I'm squashing it. I'm compressing it. And can you just trust me that that new thing is 1/3 the height of the old one? Okay. So I hope that gives you a visual of what we're talking about. Horizontal stretches result in the new graph being either wider or narrower. So we have a horizontal stretch factor. And the same thing holds as what I just said about vertical. Except that if we have a stretch factor that's greater than 1, that means it gets bigger horizontally, so it doesn't get taller, it gets wider. And if I have a stretch factor between 0 and 1, then it's going to become smaller in that horizontal dimension, which means it gets narrower. So that's obviously a horizontal stretch. I would indicate that using kind of a language and a diagram with an arrow there by drawing that. And it happens to be by a factor of 3. It's 3 times as wide. On the other hand, when you take a look at this is a horizontal stretch. It's what I would call a compressive stretch. It's getting narrower, and it turns out it's by a factor of 1/4. Are we fine with that language? Okay. So basically, if the stretch factor is bigger than 1, the graph grows in whatever dimension we're talking about, and if it's between 0 and 1, it shrinks in that dimension. So let's take a look at the warm-up on the next page. What we are asked to do in this warm-up part A is stretch this function vertically by a factor of 2. Now, what that means is we're going to redraw the whole thing, but it's going to be twice as tall. We have to come up with a consensus here as to what we stretch things relative to. And just like reflections that are vertical are relative to the x-axis, so are vertical stretches. Reflections and stretches that are vertical are relative to the x-axis. So what this means is every point on this graph needs to be replotted so that it is twice as far away from the x-axis as it currently is. So normally I would say let's start on the left and move to the right, but I want to save that point just for a minute. Let's talk about this point. This point vertically is 2 units away from the x-axis. So when I plot it after a vertical stretch by a factor of 2, it will be 4. It's twice as far away from the x-axis because the vertical stretch factor is 2. This point is going to be invariant. If a point is above the x-axis in this scenario, we have to plot it twice as far above. If a point is below, we have to plot it twice as far below. So, in other words, then, I guess it's a logical conclusion that if a point is on the x-axis, it doesn't get stretched at all. And we can draw a line connecting these, of course. And continue on our little journey. So we go to the next point, which happens to be 4 above. I double 4 because the stretch factor vertically is 2. That takes me to 8. And I just continue doing this. It's not a arduous task, not a complicated thing. Stretch vertically by a factor of 2. You could plot all of the points and then worry about connecting them. I just find that systematically doing this is a little easier. And then finally, we can take this point, which is 4 below, and it will be 8 below. And we can connect these two. And if you've done a decent job, you will notice that there's a point on the x-axis of intersection between the two functions, the original and the stretched. And that point is a point of intersection because that would be an invariant point. So what are we asked to do? We're asked to circle the invariant points. This is an invariant point. This is an invariant point. And write the mapping. So what has happened here? It's really quite simple. Y has been multiplied by 2. If y was negative 4, it becomes negative 8. If y was 2, it becomes 4. So the mapping is that, right? Every y coordinate gets doubled. And we can apply that mapping to the invariant points too, because the invariant points have y coordinates of 0. So if I multiply 0 by 2, I still get 0. Any questions with A? You sure? Okay. B. Well, what if we take that same graph and stretch it vertically by a factor of a quarter? Well, let's start with the mapping. It would make sense that if I'm going to take every point that's above the x-axis and reduce its distance above by a factor of a quarter, it's going to be 25% as close. You never say 4 times as close. I know there's a temptation to say that, and if this were just out in the non-mathematical classroom world, you could get away with that. We don't want to say that. We want to say 1/4 as close, not 4 times as close. If every point is going to be 1/4 as close, since the y coordinate of a point tells you how far away or close to the x-axis is, a point is, this is going to be the mapping. And we can go through and start plotting these points. This one will be invariant. This is 2 away from the x-axis, so I have to multiply the distance of 2 by a quarter, or 25%, which will take it to 1/2 away. This point is 4 away. 1/4 of 4 is 1. This is 4 away. 1/4 of 4 is 1. This is 4 away, but below 1/4 of 4 away is 1 away. And then we can connect them all. And you could connect them as you're plotting the points, or you could wait till the end. It doesn't matter. And again, notice that there is this point here that doesn't move, so these two are invariant points, and we've already got the mapping. Capiche? For A and B? Okay, so you should be able to do really C and D. I'm going to pick up the pace just a little bit here. If we want to stretch something horizontally, well, the factor is a little awkward to work with. Horizontally by a factor of 3/2, 3/2 is a number bigger than 1. It's 150%. It's 1.5. It's 1.5. Every point is going to be 1.5 times away from the x-axis as it currently is. So, for example, if we start here with this one, this point is 6 away on the left-hand side. 1.5 of 6 is 9, because 1 of 6 is 6, half of 6 is 3, 6 and 3 gives you 9. So this point is going to be over here at -9. And I hope you're cluing in to the fact that the mapping will be that the x's get multiplied by 3/2. I can take this one, which is 4 to the left. 1.5 of 4 is 6. So this line here, when it got stretched, it ended up being that red line. Moving on. This point is 0 away. So again, I don't think you need to go through this logic all the time. I'm just explaining it. If that point that I've highlighted at 0, 4, if it were to the left of the y-axis, then it would be 1.5 times further away than it currently is. But it would still be on the left. If it were on the right, it would be 1.5 times further away. Since it's on what we call the line of stretch, it doesn't move. It's going to be invariant. This one is 4 away. 1.5 of 4 is 6. We can connect these, I suppose. And this last point, I want to be careful. When I say this last point, there's an infinite number of points, right? I mean, we could be doing this to every single point that we can read roughly on the graph, but using the points that have been given to you, specified with those dots, makes it easier. That is 6 away. 1.5 of 6 is 9. So when we draw this, this is what the graph looks like. What's the invariant point? It's the y-intercept. A horizontal reflection will have a y-intercept as invariant, and horizontal stretches have a y-intercept that's invariant. The mapping will be x comma y turns to 3/2 x comma y. Are we okay with C? Okay. What we're doing here is a warm-up. This is not even really elevated to a quiz question. This is getting you used to the language of horizontal and vertical stretches. Stretch horizontally by a factor of 1/2. So this is 6 away from the vertical axis. It will be half away, like and half away. It will be half as far away from the y-axis, so it's going to be there. This point on the original is 4 away. Half of 4 is 2, so it will be there. This point, of course, will not move because it is 0 away, and if we multiply 0 by 1/2, we still get 0. Next one, 4 away. Half of 4 is 2. Six away, half of 6 is 3. So this is what we are looking at. And I hope it's clear, there is an invariant point. Just want to make sure I circled it in the previous one. I did. There is an invariant point here, and the mapping is going to be that since we stretch horizontally by a factor of 1/2, every x coordinate gets multiplied by 1/2. If x is negative, it's going to be negative, but half as great in terms of the dimension. If it's positive, x is going to be half as great. If it's 0, x is still going to be 0, so it will be invariant. All right. Now we're going to do an exploration. Now, this exploration is typed up for somebody that if they were working on this at home or following at home and watching on video, they know what to do. You do not have to do all of this. Okay, I've got the graphs loaded up. Okay, so if you were working on this at home, and I realize there's a degree symbol that I'm missing here. If you look on your handout, it says sine of x degrees. That's important. Put your calculator in degree mode and change your window settings to this. Well, I'm not even going to use a graphing calculator. I have a graphing program. So each function below is of the form y equals AF of x. Now there is a typo, 2 typos. Because when I prepared this, I'm using Adobe Illustrator and I'm copying and pasting, and I forgot to change these numbers down here. So your 2 functions below should be 1/2 f of x and 1/3 f of x, not 2f of x and 3f of x. Okay? So write the equation of each function. So each function below is of the form y equals a parameter, the parameter happens to be a, multiplied by f of x. And if you take a look, f of x is sine of x. The algebra here is simple. All I'm saying is if y is 2f of x, then this function is y, and why not write g of x equals 2 multiplied by sine of x degrees. And this function would be g of x. I mean, I hope you know, if I wanted to be technically absolutely on top of my game here, I would maybe write h of x for the next, and j of x for the next, and m of x for the next. I'm just calling them all g of x, but you should understand they're not all the same function. They're different functions, right? So g of x here is 3 sine of x degrees. G of x here, the new function would be 1/2 multiplied by sine of x degrees. And g of x here would be 1/3 multiplied by sine of x degrees. And I should have loaded up this graph earlier because I know what's going to happen when I hit it. It's going to open it, but it's probably going to open it on my monitor on the other side of the room. So let me move over and grab it. Y equals sine of x is a function that you will become intimately familiar with near the end of Unit 3, near the end of Unit 4. And this continues on and on in both directions. There's a maximum value for sine of x, here's the function, of 1, and there's a minimum value of -1. And it just oscillates up and down. And it repeats in 360 degrees. So it starts, say, at the origin, it goes up, and at 90 degrees it reaches its maximum. At 180 degrees it's back to 0 for y, then it becomes -1, and then it gets back to 0 again, and the whole thing repeats. This is a repetitive, it's called a sinusoidal function. It's a wave, it's something that we would encounter in physics. Well, if I graph y equals 2 sine of x, with a little bit of thought, you can see that it is the original function stretched vertically by a factor of 2. So, this point here that I'm going to put in green is 1 away from the x-axis vertically, and the new point after the stretch is 2 away. So we make a conclusion that 2 of x is stretched vertically by a factor of 2. Is sine of x stretched vertically by a factor of 2. We would, knowing that the universe follows patterns and it doesn't have different rules for different things that are related, we would suspect that 3 sine of x is going to be sine of x stretched vertically by a factor of 3. So we're learning something here, that a in front of f of x is a vertical stretch factor. Kind of. There's a wrinkle or a little exception to that, something that we have to take into account sooner or later. 0.5, that's the red, 0.5 sine of x is vertically stretching sine of x by a factor of 1/2. And obviously the x-intercepts are invariant because they are neither above nor below. And I focused my attention, I'm going to go back to 2 sine of x, I focused my attention on this point and this point, but I mean I could have as well focused my attention on this point and this point, or in fact any point. Every y coordinate is being multiplied by 2 in this illustration. And 1/3, I'm not sure why I didn't enter 1/3. I entered a whole bunch of 0.3s. It's not exactly 1/3, but it's close enough for what we're doing. Sine of x is 1/3 as tall. Are you with me on the effect here? Okay, so we could jump right to the conclusion, but let's answer each of these questions individually. What's happening here, and what I am about to write is not something you would write on a written response. I'm in teaching mode, you're in learning mode. Okay? What's happening here is we are stretching vertically by a factor of 2. That's what's happening. So, I mean, if you want to write out the new function is vertically stretched by a factor of 2, you can. You don't even have to write that because we're in learning mode. You have to know that that's what's happened. Over here, what's happened is things have been stretched vertically by a factor of 3. And again, that's just an abbreviation. Here, things have been stretched vertically by a factor of a half. And here, things have been stretched vertically by a factor of a third. So what is the conclusion? We're asked to describe what happens to each of these graphs, but we are also asked to write a conclusion. And we can't use arrows here because A could be a number bigger than 1 or between 0 and 1. So it's best to just say that the new function which is g of x or y equals a f of x is f of x stretched vertically by a factor of, now I don't want to say a, even though you'll be sitting there going, well, it's a. Because the stretch factor is always a positive number. And the fact of the matter is there's nothing to prevent me from using an a value in front of the old function of -8. I can do that. But what I'm going to do instead is say the absolute value of a. And you should remember from Math 20 that the absolute value means just knock off the negative if there's a negative there. There's more nuance than that, but that's basically it. So, you know, and I guess I can show this to you. It will only take a second. If I were to graph not 2 sine of x, but -2 sine of x, so here's 2 sine of x. If I were to graph -2 sine of x, it looks like that. So -2 sine of x is going to reflect sine of x vertically because there's a negative, which we learned about yesterday. Oh, and by the way, then it will be twice as tall. And that's why we want to use the absolute value signs in our conclusion. All right, let's take a look at number 2 for each function. Write the equation of the function. And all of these functions are of the form y equals f of bx. So this is like saying g of x, the new function, is not a number times sine of x. It's sine of a number times x. There's a difference. So this function will be g of x is sine of 2x. And I don't know if I put degrees on all of these in the previous example. It's important, but in terms of what we're learning, I guess it's not. I'll put it this time just in case I forgot to do it last time. And this will be sine of 3x. It's going to bother me now. I'm just going to go back and look. I put degrees on all of them. It's fine. This will be the new function is sine of a half x. And this will be the new function is sine of a third x. And now we want to graph these. So we already know what y equals sine of x looks like. And I know, for a fact from experience that if I asked everybody to make a prediction about what sine of 2x looks like, most people will get it wrong. I don't know anybody who will get it right unless you just guessed. Because you see that 2 in front of x and you think, oh, things are going to get twice as long. They won't. It's stretched horizontally by a factor of a half. This blue function has been squished horizontally. And to help you visualize this, maybe what I will do is put this into my notebook software so I can highlight some things. So the pink function is the original function. I don't normally like using this highlighter, but it matches. So this is the original function. And I'm just going to refer to the stuff that's on the right of the y-axis. And if you take a look at it, it goes through one complete wave, one complete up, back to the middle, down to the bottom, back to the middle in 360. But that now, when you look at the original compared to the new one completes one complete wave in 180. It's like I've taken this right here and I've locked this origin in, and I've leaned on this point that's green to the right, and I've squished it so that it's half as long horizontally. So let's just pause for a second here and write that conclusion, not conclusion, but write that statement about this function. Things have been stretched horizontally. They have been stretched horizontally, not by a factor of 2, but by a factor of a half. And I don't know that I will ever really explain to you why the opposite is happening here. If somebody wants to know, I would be happy to explain it to you. Briefly, and this isn't an explanation, it's very similar to the fact that when you have x minus h, you do the opposite to the graph of what minus h is, because it's with the x. So here, whatever you're doing to x, the opposite happens on the graph. And the opposite of multiplication is division. Okay. We could make a prediction here that this will be stretched horizontally by a factor of a third, and our prediction would be right. And what we should see then is that one complete wave that goes from 0 up, down, up, back to 0 vertically. That one complete wave that does that in 360 should do it in 120, because a third of 360 is 120. And it does. So that wave from 0 to the end of my view here is happening 3 times instead of just once, because it's 1/3 as wide. 0.5x gets twice as long. And 1/3 x, sine of 1/3 x, if you were to track some points here, you would discover it's 3 times as long. The distance horizontally on the pink graph to the maximum is 90 degrees. But the distance from the origin to the peak max on the green graph is 270. It's 3 times greater. So this will be stretched horizontally by a factor of 2. Well, will be. It is stretched horizontally by a factor of 2, and this one is stretched horizontally by a factor of 3. And as much as I said in the very first day when we were talking about h and k, some of you were going to stumble. There's going to be a lot more stumbling here with this b thing. Okay? There will be. Write a conclusion about how f of x is transformed when we create g of x equals f of bx. The answer is, and I'll abbreviate this just slightly, there will be a horizontal stretch of 1 over the absolute value of b applied to f of x. Don't let the algebra of that 1 over the absolute value of b knock you around in your head. All it means is take the reciprocal of b, and if there's a negative, get rid of the negative. You don't even have to. If b is a half, For goodness sake, you don't have to do this. Don't have to confuse yourself. 1 over a half is the reciprocal of a half, which is 2. You just flip it over, that's all. Okay? And the absolute value is there because we could reflect things horizontally. So, a conclusion, a summary is on the next page. And then we're going to do just a few examples together. The y-coordinate in a vertical stretch is multiplied by some positive number, which we call the vertical stretch factor. And during a vertical stretch, the x-coordinate does not change. This is from the warm-up. We learned this on the first page of this lesson. The equation of the function, which we learned just in the last part, the exploration, is that f of x changes to a times f of x. And whether you choose to use y equals for both or g of x equals for the second one is entirely up to you. The vertical stretch factor is equal to the absolute value of a. If a is negative, there also happens to be a vertical reflection. Okay? That's just tying together what we learned yesterday with today. The mapping, be very careful here, is that y turns into a times y, not the absolute value of a times y. If a is negative, we want to multiply y by that negative number, because the negative part of a will flip that point vertically for the vertical reflection, and then the number itself without the negative will be responsible for stretching. X-intercepts are invariant. Horizontal stretches, well, the x-coordinate is multiplied by some positive number called the horizontal stretch factor. So let me back up here. If we take a look at this part of the exploration, this one, what, maybe better yet, what I have highlighted in yellow is the parameter b, which is the number that appears in the equation. What I have highlighted in blue is the stretch factor, which is not the number that appears in the equation. And I'm being excruciating in my explanation here, in my repetition, because I know students will mix these things up. B is a number that's in the equation in front of x. B is not the stretch factor. The stretch factor is the reciprocal of the number that's in front of x. All right, where were we? During a horizontal stretch, the y-coordinate doesn't change, and we learned on the very first page of this lesson that the x-coordinate gets multiplied by the horizontal stretch factor, which is not b. It's not b. The equation changes from y equals f of x to y equals f of bx, or g of x equals f of bx. The horizontal stretch factor is equal to the reciprocal of the absolute value of the parameter that's in the equation. So if there's a number in front of x that's negative, to talk about the stretch factor, ignore the negative and take the reciprocal of that number, and that will be the stretch factor. If b is negative, there's also a horizontal reflection. And by the way, with horizontal reflections and stretches, it's the same kind of idea here. What happens to x is that you take the reciprocal of b, no absolute value, and you multiply by x. If b is 2, then the stretch factor horizontally is a half, so I have to multiply x by a half. If b is negative 2, then there's a horizontal stretch factor, a horizontal reflection, and a horizontal stretch by a factor of a half. So I would multiply x by 1 over negative 2. The negative would flip the x over, and the 1/2 would stretch it. So when you talk about mapping, you're not putting in absolute values. Invariant points are the y-intercepts. So examples. If I give you a function, y equals f of x, and I say, what's the equation of the new function if I stretch that vertically by a factor of 5, It's going to be 5f of x. Again, this is not an exam question. Just kind of rapid fire, getting used to what's going on. If I stretch the original function by a factor of 1/4 horizontally, well, if this is the stretch factor, this is the horizontal stretch factor. And, you know, you would never write that on an exam because who knows what somebody thinks you think it means. But I'm just teaching here. If that's the horizontal stretch factor, then b is the reciprocal of that stretch factor, which is 4. So the number in the equation in front of x will be 4. The parameter b is 4. So I want to make sure you understand something, because I can even see a student looking at what I've written here on the right and confusing what I'm saying. This is a different thing than this. I'm not saying horizontal stretch factor is b, which is 4. I'm saying the horizontal stretch factor is 1/4 and the parameter b is 4. Vertical stretch by a factor of 1/4 and a horizontal stretch by a factor of 5. This would be a good, multiple choice question where really an easy multiple choice question where this is one of your choices. This is a second choice. A third choice might be 4f of 5x. And the fourth might be 4f of 1/5 x. A 2-2 split is what I would call it. If we're stretching vertically by a factor of 1/4, then a is 1/4. If we're stretching horizontally by a factor of 5, then b is 1/5. So a f of bx, we put those parameters into the equation. We're going to have 1/4 f of 1/5 x. It's going to be this. The number that's in front of the function truly is the vertical stretch factor. The number that's in front of x inside of the function is not the stretch factor horizontally. It's the reciprocal of the stretch factor horizontally. A vertical reflection across the x-axis. I got to change this question eventually. I should not have to tell you vertical. You should be able to read a reflection across the x-axis and say to yourself, oh, that's a vertical reflection. Because across the x-axis means you go from above to below or below to above. And what that tells you is that this is A. A is 2. It's vertically reflected. Oh, well, let me back up. It's vertically reflected and vertically stretched by a factor of 2, so you would start by saying A equals 2, my mistake, but because of the reflection, A is -2. Horizontal stretch by a factor of 1/3 tells you that B is 3. So it will be g of x equals A f of bx. Again, what that means is you would just put every place in the original function, you'd put 3x, and then you'd multiply the whole result by -2. Example 2, describe how the graph changes in each of these cases. Well, I'm going to abbreviate my answers. Can you just double check to make sure that that's the same question that you have? I'm going to abbreviate my answers. There's a vertical stretch by a factor of 1/2. There is a horizontal stretch by a factor of 1/3. And there is a horizontal reflection. And again, if I were a student in this course and I were writing an exam and it were written response, I would write out the words, there is a horizontal reflection across the y-axis. I might even throw in brackets that the y-axis is x equals 0. These two things occur because b is equal to -3, and this occurs because a is equal to 1/2. Okay. Number 4, write the equation of each image or resulting function if I take y equals x squared and I stretch it horizontally by a factor of 3. So what will the equation become? Well, if I stretch it horizontally by a factor of 3, then that tells me that the parameter b is 1/3, which means g of x is f of 1/3 x. You know, this is saying f of x equals x squared, right? So what's f of 1/3 x? It's simply going to be 1/3 x quantity squared. Which gives us the new function g of x will be 1 squared over 3 squared times x squared. But there's a different thing that this brings up. There's something really important here that you are very likely to see on the diploma exam and on the unit exam, questions where you're told something happens to a function and asked, how else could the result be arrived at? And some functions, you can arrive at a new graph in multiple ways. Whatever this new function g of x looks like, I can arrive at that by taking the original function and stretching it horizontally by a factor of 3. Or I can take the original function and stretch it vertically by a factor of 1/9. Because what I have down here is g of x is equal to 1/9 times f of x, because x squared is f of x. So in this case, if you were given the graph of the original function and the graph of the new one, and you said, oh, it's stretched horizontally by a factor of 1/3, you can arrive at that by saying, I can do this, or I can do this. And here, a would have a value of 1/9, and here b would have a value of 3, but the result would be the same. If I take 1/9 times x squared, I get 1/9 x squared, which is the same as f of 1/3 x. In this case, a horizontal stretch by a factor of 3 results in the same thing as a vertical stretch by a factor of 1/9. And there are going to be many functions that we learn about down the road, particularly, well, I'll give you one quick illustration here. There's something called the logarithmic function, and it turns out that you can stretch a logarithmic function horizontally, or you could take the original function and shift it vertically and get the same thing, which is a weird thing. Stretching something horizontally compared to shifting it vertically, how do you get the same thing? Well, math is weird at times. I think we have one last example here, correct? Fairly straightforward. Y equals the absolute value of x, which means f of x is the absolute value of x. It's stretched vertically by a factor of 1/4. There's a horizontal stretch by a factor of 2. There's a horizontal reflection. I would say that if you're on top of your game and you have learned what you need to learn in this lesson, that you should be able to determine the new function g of x is 1/4 times the absolute value of -1/2 x. I'm sensing a lull across the room this morning. Is that because it's Monday, or you're just finding this very easy, or you don't know? It's just me, I guess. Do a dance and a bit of juggling or something. On page whatever we're at, the next couple of pages, there are 8 questions dealing with vertical stretches and applying them. Same as is typical for most of the lessons in this course. These questions are now exam questions. I've given you in this lesson the skills to understand stretches. Now you have to apply them to actual exam questions.